Excellent. All right. Before we get into lenses, we do have to talk about why the universe is so darn pretty. And one of the beautiful things about our universe is dispersion. I've taught you about index of refraction. Dispersion has to do with index of refraction. It turns out that not all frequencies and wavelengths of light have the same index of refraction. I know I told you that we keep it the same, and that's generally true, but here's an exception to this, right? A prism can be used, really any piece of glass, but a prism in particular can be used to spread out white light into its component colors. We haven't talked very much about color theory and perception and all that kind of stuff. We'll get there eventually, but white light is the combination of all the colors. And when I'm talking about white light, I'm talking about like projected light, the light that comes from the sun, the light that's on the screen. When you're working with pigments like in paints, so you say you're doing art or painting a wall or something like that, pigments don't behave like this. If you take all the colors of all the paint buckets and you throw them on the wall, what are you going to get? You get like baby poop brown. It's usually the color that you end up with, right? So the pigments are different. Pigments are all about absorption. What we're talking about is projection of light. But white light being the combination of all the colors, right? Prisms can take them apart, and the way a prism takes it apart is through this process called dispersion. Red light bends less than blue light, and the reason being is that the actual index of refraction is different for different colors, different frequencies. The higher the frequency, which high frequency corresponds to like blues, violets, that kind of stuff, they have a higher index of refraction than the reds and oranges and yellows of the spectrum. And so what we end up having here, right, is this kind of fall off in index. But what it means is the higher the index, the more bent that frequency is going to become. And so white light being a combination of all the wavelengths and all the frequencies, when it refracts and starts to bend through a change in medium, the blue light's going to bend more. There's going to be more angle there than the red light. And this idea is called dispersion, because everybody wave at the dean. Oh, she didn't see. Okay. You have this spreading out of the light rays. They're dispersing the frequencies and wavelengths into different angles. Now, the reason I'm talking about this, and the reason this is such a good idea for today, has to do with rainbows and dispersion in water droplets. Rainbows happen because of this feature of the index of refraction and how light interacts with materials. For a rainbow to form, you have to have a very specific set of circumstances. And today might be ideal for rainbow formation. We got to see how the front sort of passes through and what happens, okay? But sunlight needs to enter a raindrop. And then it needs to do a few things. So like in this picture right here, we can see sunlight entering the drop from the top of the drop. And we're modeling perfectly spherical drops, but raindrops are more raindrops. They're amoeba shaped. They get weird, okay? But generally this works for just about any shape. So sunlight comes in the top. The sunlight begins to disperse, meaning the blues and reds and everything in between spread out. We'll get some reflection off the back. There is some refraction there, by the way, but there's a little bit of reflection. And then it comes out the bottom of the ray, and as it comes out, like as it travels through the material, it kind of disperses further and further and further, right? And then when the light comes out the bottom of the drop, we will have the blue end separated from the red end with all the colors of the rainbow in between, okay? So this is for one drop, right? Put a lot of drops together and you get this phenomenon. So let's kind of lay out the geometry of this. If you're going to see a rainbow, where does the sunlight need to be coming from? Like if you're standing here and you're seeing a rainbow over there. Where's the sun? it has to be behind you, right? The sunlight needs to be coming kind of like over your shoulder, entering the tops of raindrops, and then coming back, excuse me, to your eyes. So the phenomenon of a rainbow, when you're standing on the ground, really can only happen when the sunlight's coming over your shoulder. What's the only 2 times of day that sunlight is going to be kind of coming horizontally over your shoulder? Yeah, it's dusk or dawn, right? It's sunrise or sunset, or close there too, right? Like an hour before sunset, an hour after sunrise, the sun will be low enough on the horizon for the light to be coming behind you. So in order to see a rainbow, generally you see them, most often people see them in the afternoon, evening, because that's when people are awake. Only insane people like me are up early enough in the morning, right, to see morning rainbows. But they do exist. So you need to be at a certain time of day. You need to have a situation, unlike right now, you have to have direct sunlight, right? So they're kind of like the sun's over there right now. There'd need to be like a break in the clouds, right? A way for the sunlight to come unimpeded, right? And then we would need a curtain, like we need rainfall to be happening, right? So this is why rainbows don't appear all the time, right? You need to have this set of conditions where you've got sort of clear sky where the sun is. You need to have rain on the opposite side, right? And the sunlight needs to be striking those drops. And you need to have enough of those drops falling with enough intensity to be able to see it. But when it happens, right? When it happens, it can be pretty cool, right? The rainbow guy on YouTube has nothing on me, right? I see a rainbow and I freak out, okay? It is just, I love rainbows, okay? And you see the red, orange, yellow, green, blue, indigo, and violet. I'm never quite sure what color indigo is. But you can see in this picture, right? See how these trees are having the sun sort of just nick the very top of the trees, right? My dad took this picture, okay, in front of their house. And so, like, the sun is behind him, right? And we're seeing the last sort of rays of sunset hitting the tops of those trees. And we're seeing that rainbow forming up in the sky, yeah? Why is it curved? I paid Jay to ask that question. Okay? It's because you are at the center of this optical phenomenon. Now let me describe the implications of what I just told you. The raindrops, right, they send out the light in very specific angles after they've reflected off the back and refract out the front, right? It turns out that this angle of separation between the dispersion that's taking place is 2 degrees. And so there's a 2-degree difference, right, in like between the red and the blue as it comes out, which means a rainbow always takes up 2 degrees of your field of view. In other words, a rainbow always appears to be the same distance from you. Okay? And, okay, that 2-degree difference, right, follows around in that arc because it's the only way that you can maintain the 2-degree difference. The 2-degree difference can't be maintained in a straight line. Okay? The optical pattern, how light is interacting with all the raindrops that are falling, but the rainbow is only seen by that 2-degree difference in the dispersion factor between the red and the blue light. Okay? And so that leaves a sort of curved shape as the result. You're sitting, okay, you're sitting at the geometric focus of an optical phenomenon, right? Which is a curve. But let's blow your mind a little bit more. It's not a rainbow. It's not an arc. It's a circle, okay? The only reason we don't tend to see the full circle is because the ground gets in the way, or you're like, well, Mr. Balogh, I've only seen a part of a rainbow, right? That's because there wasn't any rain anywhere else, right? Okay. You need the raindrops to be there, right? But the rainbow portion would only show up where the raindrops are falling. But if there was, everywhere, you would see it. if you get up high enough, say in an airplane, or this one was taken from an airplane, okay, then you will see, right, as long as you're not occluding the light. Here, this one occludes the light just a little bit, right? You can see sort of like there's a shadow a bit right here, okay? But you can see the full circle. Pilots see this quite often. A pilot, you don't need to be at sunset or sunrise. If you're flying above clouds and the sun is like 12 o'clock directly above you, right, you can look directly down, right, and the clouds will have enough water droplets in them, and you'll see the shadow of the airplane surrounded by a halo of the rainbow. So it is a complete circle, okay? But we tend to often only see the part that has raindrops, or in the case of us standing on the ground gets in the way of us seeing that full circle.
Why is there usually the mirrored one?
Okay. We'll get there. Okay. I know this is fun, right? There's so many questions about rainbows. But let me point out something that doesn't occur to most anybody, but requires a physicist to point out to you. I said that you were at the center of an optical phenomenon, right? You are the focus of the geometry, right, of the light, this interaction between sunlight and raindrops and the angles that are created by the dispersion. That means that the rainbow that you are seeing was made for you. It is your rainbow. Nobody else can see it. But Mr. Balogh, I've been with my friends, we're all like, oh, look at the rainbow. They're slightly to the side of you, right? Okay, you can't put your eyes in exactly the same space as another person's eyes. What they are seeing is their rainbow, created by the same sunlight and the same raindrops, right? The situation, the environmental conditions are all identical. But every person that sees a rainbow is seeing the rainbow that was created for them. When you see a rainbow, that is your rainbow. Live in it. Appreciate it. It was made for you. Right? And only you. Somebody else might be seeing a rainbow. You can't see theirs. They can't see yours. It's all you. Okay? Now, Evan asked, what about the second rainbow, right? Sometimes there's a double rainbow. Well, do you remember where I said the sunlight enters the raindrop on the other slide? It was the top, wasn't it? Well, what happens when the sunlight enters the bottom? Right? So this picture, I'm guaranteed that this picture was altered just slightly, okay? Generally, the second bow is really faint, right? And our eyes can kind of pick it up, and if you trick a camera, it can pick it up. You can increase its sensitivity. That's kind of what they've done here. I'm not saying they photoshopped it. I'm just saying they upped the sensitivity to really get the strong second bow there, because the initial bow really is usually not that bright or that strong. When the sunlight enters the bottom of the drop, okay, there's another set of optical paths, bounces, phenomenon, where the light comes in and does a double bounce off of the interior of the raindrop before it gets back to your eyes. So through the top of the raindrop is a single bounce. It's a bounce off the back and then refraction out the front. Here with the second rainbow, it takes a double bounce. And that geometry puts it, right, in another spot. And this is what I would call more accurate, okay, to kind of the perception that most people have for that second bow. Do you see how really just kind of faint it is compared to the primary? At every bounce in that raindrop, there's reflection and refraction. And a lot of energy, for the first bow, comes in through the top, right? And then as it goes and bounces off the backside of the raindrop, there's a lot that gets transmitted, okay? I can't remember what percentage it is, but it's like above 70% of the light energy escapes out of the raindrop for you to not see. And then a very small portion gets reflected. because it's 2 bounces for the secondary bow, it's even fainter, right? Let's say you lose, I don't know, 80% of the intensity, right, on the first bounce. Well, now the second bounce, you're going to lose 80% of the remaining 20%, right? Like it just keeps chopping it down. And so that's why that second bow is much fainter. Because it's a double bounce, it's also reversed in its colors. Do you see how this rainbow is red to blue, red on top to kind of blue on bottom? It's reversed for the second bow, okay? It's blue on top, red to bottom. Because again, it's bounced twice, law of reflection. The first one's an inversion, the second one is an inversion of an inversion, which is we're back to normal, okay? Again, depending on sort of how the light is lining up, right, that second bow can be more or less intense. It's just a question of how dark it is, how occluded the sun is. There's lots of stuff going on. So if we're going to see rainbows today, so optimal rainbows, right? It needs to be raining, okay? It needs to be near sunrise or sunset. And like wherever the sun is in the sky, it needs to be clearing, right? So if we're going to see rainbows today, and I'm already primed to be looking for them because it's raining. Anytime it's raining, I'm like, rainbow hunt, okay? Today, because right now the sun is completely occluded, it's completely overcast, 100% overcast, I'm going to be looking closer to sunset, right? So sunset tonight is at 6:23 p.m., okay? So starting around 5:30, right, I kind of be keeping my eyes out, right? Especially if on the western side of the sky, it's clearing up. Now this system is supposed to push through today, and about like 2 or 3 in the afternoon, it should kind of start clearing a little bit. It kind of depends on how much it stalls out. But over the Sierras, it's going to continue to kind of pile up because of orographic lifting and all that sort of stuff. And so there's a good chance that we're going to have a little bit of sunshine coming through on the western side of the sky, and maybe a chance of some rainfall happening over here in the east. Again, it kind of depends on how fast the front moves through. So around about 5:30 tonight, wherever you are, if you can peek out the window, if you're walking around, whatever that's happening, right? Just maybe see, right? Again, it needs to be raining over there, right, in the east. We need clear sun in the west for any chance of it to be happening. Sometimes you can see rainbows, like if you're driving along and the lights are on in your car and the car in front of you is kicking up a lot of mist. In that mist and from the lights of your car, you can see kind of a rainbow. Anybody that's ever taken a garden hose and put it on the mist setting, right, to mist some plants, if it's bright sunlight out and you turn it on and you get that cloud of droplets, you'll see a rainbow in that cloud, right, like mini rainbows. It's still taking up 2 degrees of your field of view, right? So no matter what, it kind of looks the same size. It's just, raindrops far away versus mist up close, it'll appear bigger or smaller. The other thing that you need to understand about rainbows, right, because you are at the center of the optical phenomenon, is that a rainbow will move with you. I've been driving on the freeway, driving along, heading north or south, right, and a rainbow forms in the east and the west, and then I'm driving along, right, carefully, I'm paying attention to the lanes and all that kind of stuff, right, okay? You can look off to the side and the rainbow will track with you, right? Again, you're at the center of that optical phenomenon, right? And so eventually you run out of raindrops, you don't see the rainbow anymore. But because you're at the center of the rainbow, this optical phenomenon, the rainbow tracks with you. As you try to get closer to a rainbow, if you try to walk towards the rainbow, what's the rainbow going to do? It's going to move just as fast, right? So the other implication of this is that leprechauns are really smart. Because where do leprechauns store their gold? At the end of the rainbow, right? You can't touch it. Somehow they can, but you can't. And for those of you that don't know, leprechauns are sort of, they're fey spirits, or they're not evil, but they're kind of trickster spirits in Irish mythology, Gaelic mythology. Not Gaelic. What are all those Scottish and Irish people called? Gaelics or the Italians? I can't remember. I'm not a history person, so nor do I know anything about mythology. That's not true. I know a lot about Greek mythology, but that's because of astronomy. If you want the world's best soap opera, study Greek mythology. All right. Let's tackle lenses. There should be enough Did everybody get a lens? I kind of put one out on every spot. When it comes time, when I call for them to come back, if you guys could help me by grabbing the ones that aren't spoken for, we'll put them in the containers. But let's talk lenses. Okay, so a lens is refracting light. Mirrors reflect and use the law of reflection, but a lens uses the law of refraction. And a lens can bend light one of two ways. So we're gonna simplify here with our lenses. Okay, a lens is either going to be a concave lens. Okay, a converging lens, when the outside of it bows out on both sides. It's called, I think we call it you can either call it a biconvex or a dual convex lens, right? It's like both sides of the lens are curving, right, outwards. That's called a converging lens. That's the picture at the top. A diverging lens is two concave surfaces on either side of the lens. In truth, like if you wear eyeglasses or something, you can actually kind of do a converging, like a convex side and a concave side, right? We're not going to get into this kind of lens. Our lenses are either going to be like bowing out, which we call converging, or kind of sucking in, which we're going to call diverging. Those are the two lenses that we'll deal with. It's not that the others are too hard. It's just we got to introduce you to more equations and tracking more refraction. We're also going to make the simplifying assumption that the lenses we are using are thin lenses. If you make a lens really thick, you have to start taking into account other optical phenomena. So we're going to make them nice and thin, which means the light just bends through it, and all we're going to worry about is the bend. Okay, so regardless of whether it's a converging or diverging lens, it's going to have a focal length. The lenses we're going to be dealing with are spherical lenses, meaning that we don't literally cut them out of a sphere, but the shape of them is as if they're a portion of a sphere. And what do converging lenses do with the light? Light comes into the lens, where is it going to end up? At the focal point, right? On the opposite side of the lens, okay? And a diverging lens, what does the light do? Light comes in, and instead of coming to the focal point, what's it do? It spreads away from a focal point. Lenses also have two focal points. There's a focal point on the front and a focal point on the back, okay? And so this brings up the whole concept and idea of these conventions. So I gave you the piece of paper, right, that had the sign conventions on them. On your piece of paper, they're both there, right? I never know how to handle this. I can never remember what I did last time. Tell you what, I'll try to remember to put the convention table on your exam somewhere. Okay? So what that means is you don't, because people ask me, like, Mr. Balogh, can I bring, can I just bring the little sheet in addition to my cheat sheet? Well, now I got to worry about whether or not people have extra things on the sign convention sheet, all that kind of stuff. At other times, I've handed out copies of those things, and that kind of. I'm going to try to remember to put it on the test somewhere, maybe the back page, right? We'll just have the sign conventions on. So what I'm telling you is you don't need to worry about putting it on your cheat sheet, right? I'll have these exact sign convention things on the test somewhere, and when I forget, I'll print them out and hand them to you. All right, choose. Always have a backup because you know you're an idiot. and we'll forget things. There we go. For some reason, this crashed, but I brought it back. So I got to make sure it's changing. Nope. Sometimes the OBS gets screwed up too. Okay. Now it's working. Okay. We're back to normal. Okay. So notice there's some changes here, and I've warned you. I've kind of been warning you about this, right? That the sign conventions go weird when it comes to lenses. In mirrors, it was pretty straightforward, right? If it's on the front side, it's positive, right? It's on the back side, it's negative. Doesn't matter what's going on. The front side of a lens is always the side that the object is on, by definition. Which makes this chart already a little weird. Because how could you ever have an object on the back side of a lens? If the front side is always the side that has the object on it, right? How could you possibly have a negative? For a single lens, it is impossible. But for a multiple lens system, now it's possible to have objects on the back side of a lens. I want to get into, we're going to do some multiple optic systems, but like in the context of making like a camera or a microscope or a telescope. We're not going to actually kind of do a whole bunch of ray tracing or math for that. So for all intents and purposes, object distance for every lens is going to be positive. We're just going to say that because the front side of a lens is the side with the object on it. In the case of mirrors, the front side was the shiny side, right? Whatever the shiny side was, and obviously you had to have the object on the shiny side, otherwise nothing was happening, okay? But it can get a little bit squirrely with lenses. Okay, notice though, if the image ends up on the same side as the object, that image distance is now going to be called negative. Image distance is positive when it's on the back side of a lens. Again, lenses are all about sending light through them, which is the reason for these conventions. Our shape of lens, whether it's converging or diverging, tells you whether or not you have positive or negative focal length. I try to remember that diverging lenses spread the light out, and so it's like a negative feature, right? I always think of a lens as bringing light together, focusing things down, and so a converging lens is positive, and then any lens that spreads light out has a negative focal length. And that focal length, right, there's two focal points to a lens because lenses are double-sided. The magnification, thankfully, is the same, right? Upright or inverted, plus or minus. So let's go through some examples of this, right? I want to do kind of like what I did with mirrors, where we went through all of the possibilities, right, for what could be happening. I want to go through all of the possibilities for various kinds of lenses. So we got two lenses to tackle and all the situations that it could be. Let's go back real quick to the simulation that I shared with you, okay? And this time, instead of picking mirror, we're going to pick lens. And we're going to pick, of course, the arrow. You can pick the penguin. Make sure to always set it to the principal rays, right? And if it bothers you that the lens isn't touching all the rays, you can make the diameter bigger. That actual diameter just changes the graphic. It doesn't change the physics of the situation. All right, and let's bring, I don't know, I just kind of like to bring that one down. All right, so now, right, I can move this back and forth. Okay, these yellow dots right here are the focal points. Again, two focal points, because a lens, unlike a mirror, which just has one side, a lens has two. You can see here that the three principal rays for the ray tracing diagram, right? One goes parallel and then passes through the focus. Another one goes through a focus and then parallel, and the other one goes through the center of the lens, right? If we trace those down, let's talk about like what kind of image we have. Is it real or virtual? And how do you know? It's real. How do you know it's real? real rays converged, right? There's no dotted lines, but a ray that left the object, went through the lens, right, converged or came over the top of each other. And so real rays being present means it's a real image. In other words, I could come in and like block these lines, say with a piece of paper or my hand, and it would cause the image to disappear, right? The test for real or virtual is always, can you put something in the way that causes a problem, right? I know this is a real image on this screen because I can occlude it. I can, like a shadow appears, right? If this were a virtual image, I put my hand here, you'd still be able to see it. Just like in your bathroom mirror, right? You can go and wave your hands behind the mirror and it doesn't change what you're seeing in the mirror, right? Because the virtual rays can't be, the only place virtual rays exist are in your head. Okay, so I've got my object outside of my focal length, right? And it's a real image, upright or inverted. It's inverted, magnified or reduced. This one looks reduced, doesn't it? Okay, but as I get closer to the focal point, look at what it does. Do you see how it's getting bigger and bigger and bigger? It stays inverted, it stays real, but it's like the closer I get to the focal point, right? The further like away I get, it starts, so far away it starts small, and then eventually, again, at the center of curvature, it's equal, and then as you get closer. Okay, but notice now what happens when we pass inside the focal point, right? Now we have a virtual image, okay? So in order for a real image to form, we have to be outside the focal length of the lens. In order for a virtual image to form, for a converging lens, right, we need to be inside the focal point. All right, if we switch to diverging, it doesn't matter where we put this thing, right? Whether it's inside the focal point or outside the focal point. What kind of image are you always getting? It's always virtual, right? Diverging lenses can only create virtual images. There's no other way to do it, okay? When it comes to converging, it depends on where the object is in relation to the focal length. If outside the focal length of the lens, it's going to be real. If the object moves inside the focal length of the lens, then your image is going to be virtual. All right. Let me switch back. Hope my technological house of cards stays up. Okay. So let's take your magnifying glass, okay? I want you to see the difference between a real and a virtual image, okay? Use a magnifying glass the way you would use a magnifying glass, right? If you look through it, like at your hand or at your notes or something like that, what's the image? Upright or inverted? It's upright, okay? Magnified or reduced? It's magnified. Real or virtual? In this case, it's virtual. Well, we'll do it. We'll do the math for this, okay? We'll do the diagram for this. But what you are looking at when you're using a magnifying glass is a virtual image. An image that's forming in your brain, okay? I saw that, Jay, right? You're sitting here, oh, look, I can occlude it. No, which side is the front side of the lens? Is it the side with my hand or the side with my eye? It's my hand. This is the object that is being looked at, right? What side, where do I see the image of my hand? Do I see the image of the hand like in front of the lens or behind it? Yeah. So the image ends up on the front side. Remember where the front side is? It's not where your eye is. The front side is where the object is, and the image seems to be over here as well. And so I have an image that's forming on the front side, and as you'll find out, that's going to be a virtual image. Now take the same magnifying glass, and instead of doing hey, it looks bigger, I want you to hold it out at arm's length, okay? Hold it out at arm's length and look across the room. You need to be looking at an object that's pretty far away, okay? Look at a corner of the room, look at an opposite wall, something like that. Now what do you see? It's an inverted image. Mine looks reduced, right? Like the people look, oh, you guys look pretty funny, okay? They look, right? This is an inverted, reduced, real image. Like, how do you tell the difference between real and virtual? Like by looking at it. Because where is this image forming? On the front side, which is opposite my eyeball, or the back side? It's forming on the back side. This image that I'm seeing is forming somewhere like right here-ish. Okay? And so I'm not seeing it on this side, but it can be really hard to perceive. You could sit there for a while going, I think it's on the back, right? It's on the other side, right? It's not, okay? Especially virtual images, which form where? In your brain, right? Everybody's perception of it is going to be different because everybody's brain is different. Everybody's visual system is different. There's commonalities, but individual perceptions depend on how well or how your brain has learned how to interpret what's going on. So an actual just like visual inspection, it can be really hard to tell whether the image is real or virtual. A ray trace diagram followed with a calculation is really the best way to determine whether you've got a real or virtual image. So let me see if I can't demonstrate that for you. Okay, yeah, we did that. Okay, so the equation, by the way, for all of this, let me go back to the sign conventions. I probably should have put it here. Okay, it's the same equation that we had for mirrors. It's just a happy coincidence, by the way, okay? The physics is slightly different, but the math ends up being the same. Magnification, same equation that we had before, okay? So we're just recycling the same math, right? We just got to be careful about the conventions. What sign are we going to put on things, right? What's positive? What's negative? What you don't want to be doing in any of this is guessing, right? You want to be applying correct signs according to the sign conventions. Otherwise, the equations do break, right? Okay, so let's do the converging lens. And for the converging lens, I'm going to use my favorite focal length of 15 centimeters. For a converging lens, is it a positive or negative focal length? What's the sign conventions tell us? It's positive for a converging lens, right? How do I tell that this is a converging lens? Rays, what are rays doing? They're focusing down, right? They're converging. They're coming together on the other side. That's how I can look at the diagram, tell whether it's converging or diverging by looking at what the rays are doing, okay? So 15 centimeter focal length, and that 15 centimeter focal length is definitely going to be positive. Let's put the object at, I did 25 centimeters in my notes for whatever reason, okay? And let's calculate where it is. Let's find the image distance, right? We did the math yesterday for all of this. It turns out to be this, if you do the algebra. So let's see. That's 1 over a positive 15 minus 1 over a positive 25. How did I know that the object was on the front side? What's the front side of a lens? The side that the object's on, right? So again, it always has to be positive for lenses, as long as it's a single lens, right? All right, and then I've got to invert all of that. When I did that, I got 37.5 centimeters, a positive 37.5 centimeters. So I stop for a second and I start asking questions, right? First thing I'm going to ask is that sign, that positive sign that's right there. According to the sign convention chart, how do you get a positive image distance? Where does the image have to be? It has to be in the back, right? According to our diagram here, is the image forming on the back side of the lens? Yeah, okay. So I expected to get a positive sign there. It's a good check to make, right? All right, magnification. Negative image distance over object distance, so that's negative 37.5 divided by 25. This is going to be a number bigger than 1. It turns out to be negative 1.5, okay? What's the negative sign mean on that magnification? It's inverted. Does our ray diagram say that it's inverted? Yeah, it's upside down, right? So we know it's inverted. We know it's magnified in this case. You really can't tell from this picture, right? And then what else do we know? Real or virtual? I mean, the diagram says real. Not every diagram says real, right? But how do you tell that it's real? Real rays need to be converging. Like light passes through this lens and bends down to form the image. Actual real light rays, not ones that are invented by your brain. If I was going to throw a little tiny sketch on my cheat sheet, right, for this one, by the way, I always draw lenses as straight lines, okay? If you want to, you can draw like the bowie out parts or whatever, but I don't, it actually doesn't matter what the actual curvature of the surface is when you're drawing the optical diagram. All that matters is the plane of the lens. For mirrors, it matters what the curvature is. But again, we're just doing little sketches. I'd put a plus F, right, just to indicate it's a converging lens. I'd drop my focal length points, which are the equal distance on both sides. And then I would just draw like a little sketch, right? And basically, my sketch would just maybe, I mean, you don't even have to do all of the rays, right? But you would draw a sketch, and basically it would you kind of just do this, right? And maybe, real image, right? Just again, give yourself an idea. We did the situation where the object was located outside of the focal point. We did the simulation that showed no matter where we moved this object, we always got a real image on the other side. The next condition, or the next difference that we would have, is when this object moves to inside the focal length. And when you do that, you get this diagram. So again, like a quick sketch that I would put on my cheat sheet, right? I'd have focal. It's still a converging lens, right? But now the object is inside the focal point. And so I would draw like a virtual image over here. And you can kind of, if you want to draw some stuff. But you don't really have to. I just need enough of a reminder, right? That this is a case where anytime the object goes inside the focal length of a converging lens, I'm going to get a virtual image. So how do you get a real image in a converging lens? Object has to be outside the focal point. How do you get in virtual image? It has to be inside the focal point. So back to our little experiment here with our magnifying glasses. When you're holding it out at arm's length and you get that real image, where have we put the objects? Outside the focal length, right? But when we use them as magnifying glasses, okay, we have to put our hands or our books or whatever really close to the lens. What do we now know about where this object is? It's inside the focal length of whatever the focal length of this lens is, right? All right. So what does the math tell us, right? Okay, first of all, if I said that the focal length was 15 centimeters, is it positive or negative? What kind of lens is this? It's a converging lens still, right? We haven't changed the type of lens. We've just moved where the object is located. So what is the focal length of a converging lens, positive or negative? It's positive according to our sheet. Okay? Distance to the object, in my notes I did 10 centimeters. So let's go and calculate the image distance. 1 over f minus 1 over do inverted. So 1 over, again, plus 15 minus 1 over 10 minus 1. I go into my calculator. I ask it what this number is, and it tells me it's negative 30 centimeters. What does the negative sign mean on image distance? What's the convention say? A negative image distance is forming on the front side of the lens. Well, this is the front side. How do I know that that side is the front side of my lens? The object's over there, right? Okay. This is where my object is. This has to be the front side. This is the back side, right? Where is this image forming? Same side as the object, which means it's on the front side, which means the negative sign is correct. The actual number diagram can't help you there, right? So you just kind of have to hope that your calculator did it right. All right, magnification. What are we going to get, by the way? Let's just predict what the magnification is going, like not the number, but like what sign is it going to be? Positive or negative magnification? How do you know it's going to be positive? It's upright. You see how the image is upright? Okay. Magnified or reduced? Greatly magnified, right? So I expect a positive answer that is a ratio bigger than 1. Just looking at the diagram, right? So magnification, negative image distance over object distance. So that's a negative 30 all over 10, which is a positive 3, isn't it? I got the positive magnification because it's upright. And I got a magnified image because I got a ratio bigger than 1. Right? So my ray trace diagram and my math are in agreement here. Okay? So that was the second of the 3 cases you can have with lenses. So again, just to review, with a converging lens, we can have an object outside the focal length, in which case you're going to get a real image. You can have an object inside the focal length, in which case you're going to get a virtual image. And the third case is the diverging lens. Okay? A diverging lens will only form virtual images. I said this before, right? The reason a diverging lens can only form virtual images is by definition a diverging lens spreads light out. And if it's spreading the light out, that means real physical rays can't converge. They're spreading out or diverging from each other. And so the only image that's going to form is one that is formed by our brains, as our brains follow those diverging rays back to their source. So the good news about diverging lenses, doesn't matter where you put the object. It's always going to be virtual. Full stop. So if I say that the focal length is 15 centimeters, is that focal length going to be positive or negative? What do the conventions say? It's negative. Diverging lens, you put a negative sign on the focal length. If I set my object distance, I said 35 centimeters. Okay. Where's the front side of this lens? Left or right? Left side. Because it's where the object is. This is the back side. Okay. Looking at my image, I expect to get a negative image distance. Why am I expecting a negative image distance? Where's the image? It's on the same side as the object, which means it's on the front side, which means it's got to be negative, according to the sign conventions. Okay? So let's see if that holds true. 1 over a negative 15 minus 1 over positive 35. Inverted. I calculated this, and I got negative 10.5 centimeters. Okay? Again, what's the negative sign mean for image distance, according to the sign conventions? Means it's on the front side, positive on the back, negative on the front. That's where my image is. It's on the front side. Okay. All right. Magnification, negative di over do, negative a negative 10.5 all over 35. This gives me a positive 0.3. Okay. So what does the positive sign mean? Upright. Is it upright in my picture? Yep. And does it look smaller than the original object? Yeah, it does. Okay. So my diagram and my math have helped me out. So again, sort of the only sketch you need for the diverging lens, right, is this one where you've got that negative, right? You put your focal points down, you put your object, and maybe you just put your virtual image, right? And you can draw like rays, you know, doing funky spreading out from each other if you really need them, right? But it doesn't matter whether this object goes inside or outside the focal length of a diverging lens, you will always get a virtual image. Always, okay? Where the object is just determines like the magnification of it, right? How small the new image is going to be in your brain. All right, so that's like the complete tour of all the possibilities for lenses, okay? What we want to start doing now is talking about what happens when we put lenses together and start moving into what I like to call optical systems, okay? So cameras, microscopes, telescopes, the human eye, how we perceive what's going on. What does it really mean to be a virtual image? For lab on Monday, we are going to be, by the way, the lab on Monday is going to take place, a part of it, in very near darkness. To be able to like form images on our optical benches and stuff like that, if you'd be able to see it, we have to like dim the lights. So it's going to be pretty dark. I know for the 8 o'clock section, it's 8 o'clock in the morning. It's going to be dark. I'll carry you like a cattle prod and I'll just shock you awake, right? If I see you going to sleep. No, I won't do that. For the people at 11 o'clock, I know it's 11 o'clock. You still asleep, whatever, right? Like it's just, I'm warning you ahead of time. It's going to, the hardest part of the lab is going to be fighting the darkness, right? Wanting to go to sleep. So we'll be slightly in the dark, but the lab is going to have you working with both real and virtual images. And you're going to get to a point where you're just like, Mr. Balogh, I don't understand anything anymore. Like, you broke my brain. I don't get it. I thought I got it. I don't get it anymore, right? Because we're going to be messing with, again, virtual images. And where do virtual images form? In your brains. And so that means you are going to measure something different than the other people in your group. Because everybody's going to perceive the virtual image differently. It'll be good. It'll be good. Okay. When we start putting more than one lens in a system, you can get some really interesting things going on. Okay? So, general terminology that you're going to hear from here on out. Okay? When we're talking about microscopes, telescopes, the human eyeball, whatever, if there's more than one lens, there's going to be an objective lens. That's the lens that's closest to the object. So in a microscope, the objective lens is the one that's closest to the slide, the glass slide. In a telescope, the objective lens is on the front of the telescope because you're looking at an object like the moon or Saturn, right? And the lens is on the front of the telescope is closer, right, to that object. The eyepiece, you want to take a big guess as to where the eyepiece is located? It's the lens that's closest to your eye, right? In the case of microscopes and telescopes, we do not sort of take into consideration the lens that is in your eye, okay? For eyeglasses and contact lenses, we very much have to take into account the lens that's in your eye, and we'll talk about how to deal with that. But the terminology is eyepiece, objective lens, the lens closest to the object, eyepiece, the lens that's closest to your eye. These are different like pictures of the same thing. When you do multiple optics, you can break the system up into single problems, single lens, single mirror problems, okay? And whatever your image is for like your objective lens, make that the object for your eyepiece, right? So you work the problem starting with the objective lens, start working along the optical axis, and wherever you find the image for your objective, that becomes the object for the next lens in the chain. What never changes in a multiple optic system is the concept of front and back. What side is the front side of a lens? The side with the object on it. And when you have a telescope or microscope, the front side is determined by the objective lens. In other words, that is forever the front. So what happens if the first real image, in this case, the eyepiece, right? The first real image is still on the front side of the eyepiece, isn't it? But what if the first lens created an image on the back side of the eyepiece? This is now where you would have to have a negative object distance. Okay? So front is determined by the first optic in the system. You don't have separate fronts and backs for every lens in the system. Okay? Lucky for us, we're actually not going to have you like break down each optic and do like a calculation and feed that into the next one. We're actually going to simplify our equations for microscopes and telescopes to just calculate magnifications on the fly. But wanted you to have the terminology down for that. Okay? So we're going to talk cameras, we're going to talk eyeballs, we're going to talk microscopes, we're going to talk telescopes. And so let's talk cameras first, which will naturally lead us into eyeballs, and then we can start talking about telescopes and microscopes. What's the job of a camera? What do cameras do? Yeah, picture. It didn't happen, right? I can now post you. No, I wouldn't do that without your permission, right? But we pull up our phones. It's got a camera in it, right? Okay. Warning. Surgeon General's warning. I am an amateur photographer. Have been since high school, where I did yearbook pictures and photos and had to take pictures of the football team and blah, 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 right? So I've developed my own film in dark rooms. I was there when digital happened, right? All this different kind of stuff. So I'm actually going to teach you how to take good pictures today, okay? But because there's an art to it, but also a skill. But I want to make sure you understand a very, very important concept about photography. What is the best camera in the world? Actually, our eyes really stink. The best camera in the world is the one that is with you, right? I can have the fanciest digital camera with the biggest lenses, and if it's sitting at home while something's happening right next to me, it's worthless, right? So don't worry about how many megapixels your thing has or how many lenses there are on the back of your phone. Yeah, that can all change the quality of a picture technologically. But really the best camera is the one that you have, right? Because it's the one you can take pictures with. So how do you get the most out of the best camera? Well, that starts coming down to skill and understanding of what's going on. Obviously, this isn't a cellular phone camera. They do some pretty cool tricks to make sure that they can make the phone pretty thin, right? But the actual physical optical principles are the same. A camera is using a lens or lenses to take an object and get that object to form what kind of image on the film or the sensor? What kind of image does it have to be in order for the sensor to pick up anything? It must be real, right? So generally, your camera is taking an upside down picture. It kind of depends on how much glass is there, right? But generally, it's upside down compared to what you're seeing. So if you see it right side up on your screen, what has your camera done? it's flipped it again for you, okay, right? It's gonna, so you have this optical capture, right? But then we also have to have a mechanism for taking that real image and capturing it, putting it into either electrons or chemicals so that we can have a permanent picture of it, okay? The lens will contain a shutter. That's how long light is let through onto the film or sensor. It'll have an aperture, which controls the amount of light that can pass through. Not just like opening and closing of the shutter, but actual like, can we allow a lot of light in? Can we allow a little bit of light in per picture? And then the sensor. So what I'm going to do is I brought some mostly broken lenses, okay? And I'll send these around. See, does this one still? Yeah, okay. So this one lets you adjust the aperture, okay, on this, so you can see, right? You can really physically see that one. This is a telephoto lens, okay, which acts like a little bit of a telescope. And then this one also, if you look through it, you can adjust the aperture on that one. Try not to drop them, right? But pass those around, play around with them. We'll start one at the front and it'll work its way through. And then we'll start this one in the back. Make sure everybody gets to see both of them, right? The smaller one is called a macro lens. The bigger one's called a telephoto lens. Okay, in photography, they will talk about the aperture size by something called F number, okay? The weird thing is that the lower the F number, the wider opening the aperture is. You might hear Apple and Samsung and Google talking about the F number of their lens. They'll say, we have a fast optical system with an F 2.1, right? That number is indicating that the smaller the number, the more light, the wider they can make that aperture as they're taking the picture. Now, the aperture adjusts, and it does it all automatically nowadays. It used to be we had to do it all by hand, okay? But the camera will decide what to do with the aperture at any given moment. Just know that a higher F number corresponds to a smaller opening, okay? It's kind of backwards, but in photography, it makes a little bit of sense. I want to show you the effect that aperture has on the quality of your pictures. Normally, we just let this thing go automatically, right? We just take it up, pick it up, right? The best camera is the camera that you have with you, but with the advent of cameras in everybody's pocket, the average quality of pictures in the world has gone way down. Because people just go, oh, automatic, right? And there's no thought, okay, that goes into composing the shot. So let me give you some tricks to take your Instagram cred to the next level, right? This is going to like really, like people will start saying, oh, your pictures are so good. I can teach you like 2 tricks that is just going to instantly improve the quality of your pictures. This picture is dumb, okay? I didn't take it, okay? But this picture is really dumb, okay? And it's really dumb. Not only is it not an interesting like composition, like I think that food pictures posted online are exceedingly dumb. Like I really don't need to see your restaurant meal. Honestly, I just don't, right? Okay? But people feel like they just got to post everything, right? Whatever picture they took, picture of their thumb, great, put it online. Picture of their dog, great, put it online. Whatever, right? Okay? This picture definitely didn't need to get posted. But it's an excellent example of something called depth of field. Depth of field is the amount of the picture that is in focus along like the z-axis of the picture. If you look at this picture, I'm going to turn the lights off in this room. If you look at this picture, the bricks that are right next to the camera, like it kind of looks like you're standing in a doorway here, right? Or standing like in a window or something. The bricks up close to the camera are in focus. The grass is in focus. The car is in focus. The buildings far away from the camera, it's all in focus. This picture has a very large depth of field. In other words, everything is in focus. This is the default for most cellular phone cameras. They're going with this idea that we keep the largest depth of field we can. The way you pull off large depth of field is by having a high F number, which means it's a small aperture. If you're squeezing down on the amount of light that can come into the lens, then you're extending the depth of field. We won't get into the big physics of that, but compare and contrast the last picture right here, okay, with this picture's depth of field. Do you notice how the background is totally blurred? That really only this, I don't know, like dead, frozen, very depressing flower, right, is. But psychologically, even though this picture, again, what they're taking a picture of isn't terribly interesting, your brains are already going, wait a second, that looks better. Or this is a more interesting, or wait a second, something's going on here. The reason being is that pictures with large depth of field where everything is in focus, your brain is having trouble figuring out what the important part of the picture is. Is the important part of the picture the car? Is it the bricks? Is it the house in the background? Is it the grass? What's the important part of this picture? Whatever the flower is, right? Whatever the thing that is in focus. And so you can manipulate a person's perception of the picture by deliberately putting things in focus that you want them to focus on and blurring out the rest of the background. This is exactly what you want to do when you're taking a picture of a person. Portrait photography uses very narrow depth of field. Think of the yearbook photo, right? What should be in focus? The person, right? The background makes absolutely no difference because if the photographer's doing it right, the background is going to be completely blurred out. So it doesn't matter if you're standing in front of a tree, a dog, a rock, whatever, right? It's going to be blurred out because it's not an important part of the scene, okay? So that's one trick. How do you do this in your phones? Like, how do you get your phone to do that blurry background for you? It's not quite AI, it's machine learning, believe it or not, okay? But if like on my phone, which is an Apple phone, okay, if I put it into portrait mode, okay, portrait mode tries to focus on a face, it detects a face, and it makes sure that's in focus, no matter where you put your camera, and then it blurs the background and foreground of the composition, right? It's doing it through machine learning and image processing because the cell phone lens doesn't have enough glass in it to pull this off mechanically. But the effect of the picture is still the same. You're enhancing the focus of the subject, which is why when my mother-in-law says she wants a family photograph, I groan inside. Not because it's my mother-in-law, but because every time I show her the pictures afterwards, she complains about how blurry the background is. She's like, we were standing in the woods were so pretty. Then what you want is a picture of the woods, right? Not your grandkids. If you want a picture of your grandkids, I can take a picture of your grandkids. Right? I want both. Okay, then it's a bad picture. Whatever you do, don't look at my mother-in-law's picture wall because it's full of awful pictures that she's forced me to take. Notice the depth of field here. Notice how the coin, right, is in focus, but the individual matchsticks go out of focus really fast. Again, this is a demonstration. I would never suggest taking a picture of a coin like this, right? But it's trying to show you what happens with depth of field, right? This is a very narrow depth of field. This is a much wider depth of field or a longer depth of field. You see how all the matchsticks are all like in focus and the coin is in focus and all that kind of stuff? Only the ones that go way out tend to be out of focus. Also notice the picture's darker. You see how this one is lighter and this one is darker? To get a longer depth of field, the aperture has to come down. And if the aperture comes down, there's less light coming through the camera, right? So sometimes there are trade-offs to what's going on. Before we get to this, I want to give you another trick. I've taught you how to make people stand out in a photograph, or like if you're trying to take a picture of your dog or cat or something. Nowadays, it didn't used to be this way. You had to, because cell phones didn't detect animals as being like a person, right, in portrait mode. And so now they do detect like cats and dogs. If you try to do this with your turtle, it's not going to work. But they can detect a cat or a dog, right? And so when you throw it into portrait mode for taking a picture of your animal, you're going to get a really good picture of your animal, okay? Because naturally the brain will just, oh, this is in focus, everything else is blurry. Good picture of a cat or dog. Here's another way for you to get, let's see, I think if I tried to do this, I would screw up all of my recordings, so I'm not going to do it. If you open the camera, okay, I'm just going to open the camera. Let's not put it in portrait, let's put it in regular photo mode. Can you tell me if there's anything like weird or different about my camera? Like the view? What do you see that's usually not there? Do you see the lines? Okay. I've turned on a grid in the system settings of my camera, okay? And what this grid does is very difficult to see, so I'll draw it on the board. What the grid does is it divides. I should have some pictures of this as demonstrations, but I don't. What it does is it divides my viewfinder into thirds. Thirds horizontally and thirds vertically. And this is a trick called the rule of thirds, okay? If you want to psychologically boost the quality of a picture, then the only thing you need to do is put the subject of your picture where one of these lines intersects with another. So if I'm taking a picture of a person, right, in a garden, let's say, okay, and it's not like an up-close portrait shot, right? It's more of a, I'm getting the garden and I'm getting everything else, right? I would put the person's like face at one of these intersections, okay? Maybe they're looking at a tree or looking at the sky or looking at a rainbow, whatever, right? Okay, that can be over here. But I will put the thing that I want to suggest is the important part of the photograph. I'll put it at one of the intersecting lines. You should go and try this. Like, go just take a picture of your dog or cat or boyfriend, girl, whatever, right? Most people will do the picture so that the person is right in the middle of the frame. Then do exactly the same picture, but put their face, turn on the grid and put it at a spot, okay? All of a sudden, the picture will look more interesting. People will comment at how good the picture looks, and they won't be able to tell you why, okay? It's because of the rule of thirds and the psychological trick that you're playing on a person's brain to say, there's something interesting right here. For landscape photography, ignore the rule of thirds. You really don't need it. But when you're taking, like, you're trying to emphasize something in a picture and you're not using portrait mode, put it at one of the intersections for the rule of thirds. If you would please help me by picking up any of the things that you see on your way out and putting them in the blue bins, that would be fantastic. Have a great rest of the day, and I will see you on Thursday. But we'll talk about eyeballs and eyeglasses and all that kind of stuff.